Hello everyone, we are continuing the topic of transistor amplifiers, and today we are going to derive a small signal model or signal equivalent circuit model for MOS devices. Let's first review some of the definitions. Signal is something that we want to find the response of the circuit to it. Bias is the state of the system when there is no signal. Bias is constant in time. It may vary extremely slowly compared to the signal, but for the purpose of this course, when we talk about bias, we refer to the constant and DC voltages and currents in the circuit. The purpose of the bias is to ensure that MOSFET is in saturation at all times. Let's start the derivation of MOSFET small signal model using this basic MOSFET-based amplifier circuit configuration. First, let's look at the case when there is no signal applied to this amplifier. That means VGS, the signal part is equal to 0. And when there is no signal present in the circuit, I can replace it with a wire, a short circuit, and now I have a circuit configuration that we have studied in the past. Because MOSFET is going to operate in the saturation region, which is a requirement for using MOSFET as an amplifier, I have this current equation for MOSFET that is operating in the saturation region. So the drain current is equal to 1/2 Kn V over drive to the power of 2. And Kn is the transconductance parameter of this MOSFET. Also, from drain to source KVL, I have VDS equals to VDD minus RD times ID. Now, what happens if you apply a signal or small VGS to this circuit? I can write the total input voltage or total instantaneous gate to source voltage as summation of the bias part or the constant part VGS plus the signal part or small VGS. And if you use this total gate to source voltage in the drain current equation, you're going to have an equation like this. At this point, I'm going to represent the drain current with lowercase I subscript of uppercase D. That means this drain current has both a signal component and a bias component. So far in all of these calculations, we assume that lambda is equal to 0, or we neglected the channel length modulation effect. If we expand this polynomial expression, we're going to end up with 3 terms in the ID equation. The first term is the constant or DC part of the drain current. The second term consists of a constant value multiplied by the AC signal that's applied to the gate. And the third term is the current component that's proportional to the square of the input signal. The last term in the ID equation is undesirable because it represents nonlinear distortion. Now let's consider the case that this last term is much smaller than the second one. Or VGS, the signal is much smaller than 2 times the DC value of VGS minus V threshold. Or VGS is much smaller than 2 times V over drive. In this case, VGS is small enough and the small signal condition is satisfied. Now we can neglect the third term in the ID equation and write ID as summation of a bias part or constant part plus the signal part. So if the amplitude of the signal or VGS is small enough, we can approximate the drain current as summation of a DC part plus the signal part. If you compare those two ID equations, you can see that the DC component of the ID equation can be calculated using this expression, and the signal part can be calculated using this expression. The MOSFET transconductance, or GM, is defined as ID over VGS, the signal drain current over the input signal that's applied to the amplifier, and it is equal to Kn multiplied by V over drive, or 2 times ID over V over drive. And as you can see, the signal current is proportional to the input signal by a factor called GM. So there is a linear relationship between the signal part of the drain current and the voltage signal that's applied to the MOSFET transistor. Moving to the drain to source KVL, I can write VDS as VDD minus RD times ID. Here, the VDS is the total instantaneous drain to source voltage, and ID is the total instantaneous drain current. So both ID and VDS are going to have DC part and the signal part. So under small signal approximation, you saw that we can represent ID as summation of a bias part or DC part and the signal part. So I'm going to replace ID with this expression and separate the DC part from the signal part in the total instantaneous drain to source voltage, and compare it to this equation. You're going to get an expression for the DC component of the drain to source voltage, and the signal component of the drain to source voltage is equal to negative ID multiplied by drain resistor. And ID in this expression is the signal component of the drain current. I already found out how ID is related to VGS, and I can replace it here and write an expression that relates signal component of the output to the signal component of the input. So the voltage gain of the amplifier, or signal voltage gain of the amplifier, is VDS over VGS, and that's equal to negative GM multiplied by RD. So far we have seen that under small signal approximation, that means when the amplitude of the VGS is small enough, we can write the voltages and currents as summation of two terms. One of them is the bias component of that voltage or current, and the second one is the signal component of that voltage or current. That means we can find the bias component of the voltage or current separately by solving the bias circuit, and find the signal component of the voltages and currents separately by solving the signal circuit. All of the MOSFET circuits that we solved in the past consisted of only DC components, so we are familiar with solving bias circuits. In this lecture, we are going to drive a small signal model for the MOSFET and see how the signal equivalent circuit looks like for this total amplifier circuit. This picture shows a small signal model for a MOSFET transistor. In the picture, there are three terminals that represent the three terminals of the MOSFET: gate, drain, and source. ID, the drain current, is equal to GM VGS, so there is drain current flowing from drain to source, and the value of that drain current is equal to GM multiplied by VGS, so I can model it with a dependent current source. From gate to source, no current flows, so IG is equal to 0. I can model it with an open circuit, so I have VGS voltage between gate to source, and the drain current is proportional to the VGS value. We are going to complete this model by adding a resistor between drain and source, and the reason is that if you remember when we studied the channel length modulation effect, you saw that the drain current increases if the drain to source voltage is increasing. To take that effect into account, we added a resistor between drain to source and added this expression to the ID equation, and by doing so we can see that if VDS increases or drain to source voltage increases, the value of ID is also going to increase. This R sub O represents the channel length modulation effect and is almost equal to 1 over lambda multiplied by ID. Lambda is the channel length modulation parameter. As you can see, the parameters in the small signal model, which are this R sub O and GM, depend on the DC values of the MOSFET amplifier circuit. I sub D and this V over drive are the DC parameters of the transistor amplifier circuit. Looking at the total amplifier circuit that we started with, this small signal model that we developed for MOS is for the MOSFET only. So when we want to draw the signal equivalent circuit, we are going to replace the MOSFET with the circuit model that we already developed. But how about the rest of the circuit elements? How we can model them for the signal circuit? A resistor is going to remain as a resistor in the signal circuit because I can write the voltage across the resistor as summation of the bias term plus the signal term, and I know that the total voltage across the resistor equals to the resistance of that resistor multiplied by total current that flows through that resistor. From this total VR, this quantity R times I sub R is the bias component of the total voltage. So signal part can be calculated as the total voltage minus the bias voltage. That's going to give me this expression. So the signal component of the voltage across the resistor is equal to the resistance of that resistor multiplied by the signal component of the current that flows through that resistor. So if I want to draw a model for this expression, I can show it with this model. This is plus minus small v small r. This is r, and this is small I sub small r. So the resistor remains as a resistor in the signal circuit. How about the rest of the circuit elements? A capacitor is going to remain as a capacitor in the signal circuit, and unless we perform frequency analysis of the amplifier circuits, the capacitors are going to be short in the signal equivalent circuit. In other words, we're going to assume that the capacitance of these capacitors are large enough such that when we are developing the signal equivalent circuit, we can replace them with a short circuit. In this course, we are always going to replace the capacitors with short circuit when we are drawing the signal equivalent circuit. And as a reminder, a capacitor acts as an open circuit in the bias circuit because capacitors do not let the DC current or voltage go through them. A DC voltage source becomes a short circuit. In the signal circuit, when we are doing signal analysis on the circuit, DC voltage sources are going to become short-circuited because we are going to set the DC voltage source equal to 0. That means they are short. For example, if in the total amplifier circuit you have DC voltage sources like VDD that is connected to the drain, or VSS, a voltage source that's connected to the source, they're going to be effectively grounded. A DC current source becomes an open circuit because DC current equals to 0 means open circuit. Although we found a small signal model for an NMOS transistor, this model can be used for a PMOS transistor as well, because PMOS transistor, just like an NMOS transistor, consists of 3 terminals: gate, drain, and source. And in a PMOS transistor, the drain current that is proportional to VSG flows from source to drain. So the direction of arrow points from source to drain, but this current is proportional to VSG. So if I label the voltages between gate to source as VGS, just like what we had for an NMOS transistor, the direction of the current source is going to point from drain to source, and this current is going to be proportional to VGS. So we can use this model for both PMOS and NMOS transistors. So drawing the circuit model for a PMOS transistor is similar to an NMOS transistor. Finally, we would like to know how we can add the signal to the amplifier circuit. Generally, there are 2 ways of doing that. One is direct coupling. These are 2 examples of direct coupling. In the left picture, the signal is in series with the DC VGS value, and in this circuit, the MOSFET is biased using this constant current source, or this I. So using this current source, I can make sure that the transistor operates in the saturation region, and then I can directly connect my signal source to the gate of this transistor. Second way of applying a signal to the amplifier circuit is called capacitive coupling, in which a capacitor is used to connect the signal source to the amplifier circuit. So VI is connected to the rest of the circuit using this capacitor, and this is called capacitive coupling. Let's use all that we learned so far to draw the signal circuit for this example amplifier circuit using a MOS transistor. Because we are drawing the signal circuit, we are going to remove all the DC component or the bias component of this circuit. That means we are going to zero out all the DC voltage sources and DC current sources. There is no DC current source here, but I can see this VDD and negative VSS in this circuit, so I'm going to zero them out. By that I mean I'm going to short them. Also, we're going to assume that the capacitors are going to be short in the signal circuit. So I have something like this. This is my VI short here, and resistors are going to stay the same. This is the gate resistor, and this is my capacitor. So I'm going to draw it in 2 steps. At the first step, I'm not going to replace MOSFET with its small signal model. I'm going to keep it the same. So then in the second step, I'm going to complete this signal circuit by replacing the MOSFET with its small signal model. So RS is going to stay the same, and VSS, I'm going to short it, so it's going to be grounded here, and the capacitor C sub S is going to be replaced with a short circuit. From the drain side, I have R sub D, and I'm going to short VDD, so it's going to be grounded. The drain node is going to be grounded, and here I have C sub C2, it's going to be shorted, and there is a load resistor here, RL, and this is my Vout node. So this is step 1. Moving on to the second step, I'm going to replace this MOSFET with its small signal model. So this is my Vi, this is gate resistor, this is gate node. So I'm first going to draw these nodes, gate, drain, and source. There is an open circuit between gate to source, this is VGS. There is a dependent current source between drain and source, the value of it is GM-VGS. There is this R sub O that I used to model the channel length modulation effect, and because at the source I shorted the source resistor, the source terminal is going to be connected to the ground. Now looking at the drain terminal, I have RD that is connected to the drain terminal. So here is my RD. One side of RD is connected to the drain and the other side is connected to the ground. Also, I have RL that is connected to the drain terminal. So this is RL, and I take the output from the drain terminal. And this is the signal equivalent circuit for MOSFET amplifier, for this MOSFET amplifier. And if I solve this circuit, I can find the gain of the amplifier, which is Vout over Vi. To do that, I need to know the value of GM and R sub O, and I can write some KVL and KCL to solve this circuit. Since the values of GM and R sub O depend on the DC or bias values of this amplifier circuit, I need to solve the bias circuit first to find the bias drain current and VGS and V over drive, so that I can use them to find the value of GM and RO, and then I can use them to find the value of the gain for this amplifier circuit. In summary, in today's lecture, we saw that under small signal approximation, we can simplify the analysis of amplifier circuits by separating this analysis into two parts, bias analysis and signal analysis. We found a small signal model for MOSFET transistors, and we learned how to draw the signal circuit for MOSFET amplifier circuits. Thank you for watching.